Welcome back. Mechanical integrity requires that both preventive and predictive maintenance be performed on screw compressors. Oil analysis, filter changes, and motor greasing, those are all examples of preventive maintenance. The rolling element bearings in a Frick compressor allow vibration sensors to detect bearing fatigue early, predicting when the compressor will require rebuilding. Vibration analysis will reveal bearing fatigue long before any damage happens to the compressor. So many customers are interested in continuous vibration monitoring. And the PhD Plus system from Frick has several advantages. The first is precise calculations. The vibration module is configured based on the specific Frick compressor model. The module monitors the specific range of frequencies that will indicate problems with that compressor's bearings. And variable speed drives are very popular now, and the motor speed is sent to the vibration module. The motor and compressor vibration calculations adjust the monitoring window to match the actual rotation speed of the compressor and motor. With that, we get consistent readings. Because this system focuses on the bearing frequencies, it produces consistent readings across the Frick compressor models and customer applications. We have reliable detection. A one-time rotational speed calculation is used to quickly stop the compressor if a sudden vibration event is detected. The one-time rotation speed safeties are designed to recognize rapid events. Something like liquid slugging or sudden motor failure or coupling issue will be quickly and reliably detected. And fail-safe technology. Sensor failure detection is built into the PhD Plus system. The Quantum HD will indicate if the sensor has failed or if it's not wired correctly. So why is vibration analysis so good at predicting bearing issues? Frick compressors use rolling element bearings. They rotate much faster than the shaft does. So when the bearings fatigue, they'll vibrate at high frequencies. So if we see high frequency vibration in a screw compressor, it's likely coming from the bearings. Now note that sleeve bearing compressors do not have rolling elements, and thus are not as predictable in failure. And the PhD Plus is not recommended for sleeve bearing machines. The rolling element bearings make screw compressors easy to find bearing fatigue. However, you may have heard that screw compressors are difficult to analyze for vibration. And that's a true statement. Let's look at why that is. Compared to other rotating equipment, screw compressors are much more difficult to analyze for vibration. You see, both the turbine and the screw compressor work on gases, and they both spin continuously. And they're both balanced. They don't wobble. So what makes the screw compressor so difficult to analyze? Well, most rotating gas equipment has a continuous stream of gas at the inlet and a continuous stream of gas at the outlet. So any vibrations measured are caused by mechanical movement of the machine. Our screw compressor, on the other hand, has a continuous stream of gas at the inlet, but the outlet pulses. And these gas pulsations cause vibration to occur in the compressor. The screw compressor pulses its discharge. Pressure is built up in each flute and then released at discharge. Here we see the axial discharge port of the compressor, where the compressed gases are pushed out. The male rotor is driven at 3600 RPM for 60 Hz. The female rotor rides along at 2400 RPM. This is a 4-6 rotor combination. 4 male lobes, 6 female flutes, and this is typical of the RWF2 line of compressors. Other Frick compressors may use a 5-7 rotor combination. So we have 6 female flutes spinning at 2400 RPM. 2400 revolutions per minute and 6 flutes per revolution with 60 seconds in a minute. So at 3600 RPM on the motor, 60 Hz operation, the female flutes discharge 240 times per second, or at 240 Hz. And this pulsing is going to show up on a vibration analysis. And that's what makes screw compressors somewhat difficult to analyze. Let's look at a vibration graph. Here we show a graph with acceleration along the y-axis. That's an indication of just how strong the vibration is. And along the x-axis we show frequency. Well, that's the frequency at which that vibration was measured. So in this chart, we're just going to look at low frequencies, so we see the effects of the discharge pulses at the lobe passing frequency. As we plot the measurements, assuming 60 Hz operation of a 4-6 rotor profile, we can see there's a spike in energy at the lobe passing frequency, as well as harmonics, those even multiples of the lobe passing frequency. At 240 Hz, we have the largest spike. Now, if this were a VFD application, and we lowered the speed, the lobe passing frequency changes, as well as all the harmonics. These vibrations have considerable energy with them, but they are not indications of fatigue in the bearings. These all occur at frequencies much lower than the rotating elements. So let's look at the full frequency spectrum. Our lobe passing frequency has huge spikes in it, all down at low frequency. But that little spike around 7200 Hz is what we're looking for to indicate bearing fatigue. So the PhD Plus uses filters at low frequencies to block out the harmless lobe passing vibrations and uses amplifiers at the higher frequencies to increase the bearing noise measurements. The result is this. With the PhD Plus filters and amplifiers active, the benign low-frequency vibrations are muted, and the high-frequency bearing noise is amplified. This makes it easy for the PhD Plus to detect problems quickly. But that doesn't mean that there's no need for full-spectrum vibration analysis. Every Frick compressor will get a vibration analysis at startup. This gives us a baseline to compare future analyses to. Our IOM calls for full spectrum analysis to be performed semi-annually. But the PhD Plus provides continuous monitoring, eliminating the need for semi-annual analysis on compressors equipped with PhD Plus. One thing to note, however, if the PhD Plus has an alarm or a shutdown event, then a complete vibration analysis is required to determine the cause of the vibration. Obviously, the drive motor is also a critical piece of equipment that could benefit from continuous monitoring. The PhD Plus system can be used in conjunction with vibration sensors on the motor to monitor motor vibrations. However, many applications, simply rely on temperature monitoring for the motors. Bearing temperature in a flooded compressor wouldn't mean very much, because the bearings are flooded with cooled oil. Motor bearings, on the other hand, are grease lubricated, and a developing problem will generate an increase in bearing temperatures. So the PhD Plus can include motor vibration sensors and/or bearing and stator temperature indicators to monitor the condition of the drive motor. So to review, well, screw compressors are unique and have characteristic vibrations that are perfectly normal to their operation. The PhD Plus takes into account the model of the compressor and its rotational speed to filter out these normal vibrations. Continuous monitoring of compressor vibrations eliminates the need for semi-annual vibration analysis, but one must be performed if there's a warning or a shutdown. Thanks for watching, and I'll see you in the next segment.